Okay, thanks a lot for the invitation. So I'm Antti Honkela, assistant professor at the University of Helsinki and also leader of the or co-leader of the Privacy Preserving and Secure AI research program at the Finnish Center for Artificial Intelligence, FCAI. And today I'm going to talk about privacy preserving AI and differential privacy. So privacy is a very controversial topic. There's, if you go out and try one of these intelligent systems that we have, Google, you can find lots of news that used to be popular at least about how privacy is dead, and especially many CEOs of big internet companies proclaiming that we should all forget about it. This may be partly, of course, because they haven't done a very good job now in protecting it now in this era of extensive data collection about all of us. So this, of course, there's an equal number of stories where people have collected some big data sets, then done something about it that thought would preserve the privacy and anonymity of the people in the data set. That didn't turn out to work quite as well as planned. So often if you release some data, even if you think that, maybe now I've anonymized it, then people can go back, combining it with some external data, and then de-anonymizing people there. So there's lots of interesting papers like this, how you can take your internet search records, some medical data, the Netflix dataset was a very popular example, and also, so my background also comes a bit from bioinformatics side. So there, with genomes, you can do a lot, and genomic information is a very interesting topic here. So should we care about privacy? Another interesting viewpoint to that is if we go back a bit further and look into the history. There's the Universal Declaration of Human Rights that basically defines what are fundamental human rights, and this is also the basis for the European human rights agreements that then carry the force of law in all European countries. And the Universal Declaration of Human Rights has a very strong wording on this. So no one shall be subjected to arbitrary interference with his privacy, and everyone has the right to protection of law against such interference or attacks. So clearly, on some level, at least at some point in the past, there was a very strong tendency to honor privacy. Whether we are there at this time is of course an interesting question. And in some sense, I guess we can, there's been a lot of debate about what is GDPR and why should we care? Is it a good thing, or is it going to destroy all AI business in Europe? But in some sense, I would argue that, it is actually, now we are restoring privacy as it has been defined as a fundamental human right. And the examples I showed there previously was mostly about cases where you have some data, then you release data in a way that you think is anonymized, and then it turns out that, well, maybe it wasn't quite as anonymous as you thought. But what makes this challenging is that privacy is not just about the data. So machine learning, we often might keep the data to ourselves, but at least in academia, we might want to share the models, or in any other field also, we will give some access to the models to users. And now a very interesting question is, how much private information do these models remember, and how much private information can they leak? And this is a difficult question, especially if we go to these more complicated neural network models and deep learning models. So how can you tell, if you have a convolutional neural network, a recurrent neural network, or again, how much do they remember about their training data? We had a very interesting discussion about this with Leo this morning, and I guess, well, it's still, no one really knows. I have a few examples that in some cases the answer is that they remember more than you might imagine. But on a very practical level, I think privacy is an interesting question, because we ultimately have this dilemma. So the more people share their data, the better models we can develop, and eventually that will help everyone. But at an individual level, if you share your data, in some cases that may lead you to trouble, and especially maybe it's not so big in Europe, but I mean at least in the US, where kind of there's very little restrictions on how you can use this personal data. So then I guess there are serious concerns of people not being denied some insurances or whatever. So there's really, so what we would like to do is to somehow solve this in a way that you can share your data so that we can get the benefits, but in a way that we can guarantee that it will not get you to trouble. So I promised some examples of how much neural networks do you remember. So here's one classic example from 2015 about what's called a model inversion attack. So in this particular example case, this was against a face recognition system, and the attacker has access to a person's name and an access to a facial recognition system that takes a face image and then gives a classification, is this particular person or not, together with a confidence score. And using this information alone, they could recover this image from a trained neural network, black box neural network, for this person. To me, this looks a bit scary. I mean, clearly, the neural network does remember, and kind of, in case you do not want to share your facial image, this might be more than what you're willing to share. And of course, this might not be just face images. It might be other more sensitive data that is in the system. A more recent example comes from text. So this is Carlini et al. I'm not sure if it's been published. I only found the archive version of that. So they work on text models, and this is character level text models. And the assumption is that there is some known format, like my social security number is, and then you have a format here. And the question here is that then the model is basically given this format and then asked to fill in the gaps. And the training data used to train the model contains strings like this, but then including some people's actual social security numbers. And guess what happens? The neural network does what it's supposed to do. It learns the training data, and it will be very, very likely to complete this with the actual secret data that was part of the training set. So here's an example. So in order to evaluate how this the model learned these, the authors in this paper introduced a new concept that they called exposure, which measures, if you look at the relative rank of the secret that you want to hide among all possible secrets of the same type. So the base 2 logarithm of that gives the exposure. So basically, if it was random, you would want to see the exposure to be around 1 or somewhere very small. And the higher it is, it means that, in this case, we have a model that ends up with an exposure of around 30. So that means that it's 2 to the power 30 times more likely, in a sense, than kind of your average would be. And the interesting thing we see from this figure is that now they've plotted this exposure as a function of the training time together with the training loss and test loss of the neural network. And here we can see the interesting pattern that the exposure increases essentially linearly at the same time as the testing loss drops. And at the point where we have the minimum of the test loss, so this is before the model starts overfitting, that's the same time as where the exposure peaks. So this property of the neural networks to learn these secrets is not overfitting. It is actual part of the learning process. And so when the model then actually does overfit, well, the exposure basically stays there. Doesn't change. So this is, in a sense, it's a fundamental property of these neural network algorithms. So in this case, they were demonstrating this both on convolutional neural networks and recurrent neural networks. Both behave fairly similarly. And so in this particular problem, CNNs were a little worse at the task, so they were also a little worse in memorizing the secrets. But this seems to be a fundamental property of the models. In this particular paper, the authors tried a number of things in order to counter this. So different kind of regularization techniques, but none of them worked. The only thing that worked was to train the network under an algorithm that takes this privacy into account using a method called differential privacy. And that's what I'm going to talk about next. So basically, differential privacy is a framework for developing privacy-preserving algorithms, and it's especially well suited for machine learning, and it gives very strong privacy guarantees. So I'll be walking you through the basic definition and some applications of that in terms of kind of fundamental algorithms that you can do, and then also a few more practical applications of where we have used this in the research of my group. Okay, so to cut straight to the point, so differential privacy was introduced by Cynthia Dwork and colleagues about 12 years ago, and it's a definition, or it's a property of a randomized algorithm. So basically, within this framework, if your algorithm is completely deterministic, it cannot provide any privacy guarantees. Because in essence, you can't guarantee that you could just basically reconstruct whatever went into the algorithm from the output. So you need to have some randomness in the operation. And according to the definition, an algorithm is said to be differentially private with a parameter epsilon that defines the level of privacy. If, when you compare the results, when you run the algorithm on two different data sets that differ by only one sample, then the probability of obtaining any result should satisfy this condition here. So basically, it's mathematically a bit complicated, but basically it says that the probability of obtaining a result from data set D of obtaining the same result from D prime, they should be close to each other. They can't be too different. This is symmetric. I mean, it's only shows less than or equal to here, but because the definition is symmetric, so it has to work both ways. Now, epsilon is the parameter that controls the strength of this, how strict this bound is, and so the smaller the epsilon, the closer these have to be, and therefore the tighter the privacy guarantee. And the trick here is that now, so basically this says that if you change one sample in your data set, then the result can't change too much, or the probability of obtaining any specific result can't change too much. And then this gives, in a sense, plausible deniability for the data subjects. My sample was part of the data set, but you would very likely have received, but now, regardless of what my particular sample was, you would have received almost the same result in any case, so therefore you cannot learn too much about my specific sample. But now, of course, we only give this for changing one sample. So now if we look at the data in aggregate, then we can still learn something useful. And for many of these algorithms, you can actually show that they are consistent in the sense that as the sample size increases, then the results will reduce to the corresponding results of the corresponding non-private algorithm. DB provides a very strong privacy guarantee because the protection is effectively valid against adversaries, even with some side information. And this was the key to many of these attacks against these previous anonymization methods. And if you combine with some additional data, then you can break the anonymization. With DP, we essentially set a bound on how much information you can gain from this new data set. And therefore, I mean, if you have side information, then that helps, but we can basically limit how much you learn from this particular release. It is invariant to post-processing, and it degrades gracefully under composition, both of which properties make it nice to build a nice building block for algorithms. So we can construct very complex algorithms around this. Before going to these very complex algorithms, I'll start with a very simple one to give you an intuition of how this works. So maybe the simplest possible DP mechanism of randomized response. So this is something that has been used by social scientists already way before the introduction to differential privacy, but it happens to fill this definition as well. So the setting is that we assume that we want to ask some respondents some sensitive question. Let's say, do you use illegal drugs? Most people would not want to answer that question publicly, or even in secret to some one who's making this study. So, in order to give them privacy, we would instruct the respondents to follow the following protocol. So first, you start by flipping a coin. If you get tails, then you respond truthfully. If you get heads, then you flip a second coin and answer whatever that particular coin told you. So this now introduces randomness into the responses. And this also gives this plausible deniability idea that, I mean, even if you say yes, you can always say that, well, it was just a coin. I'm not really using drugs, but it's just following the protocol. But now, of course, there's still some useful information we get out of this. So there's a 50% chance that people will just answer noisily, but there's a 50% chance that they will answer truthfully. So now if we take a look at the proportion of people who answer yes, so on average that will be 1/2 plus 1/2 the time of the proportion in the population. So with enough respondents, we can then actually recover an approximate proportion of how many people are actually using illegal drugs. And as I mentioned, this mechanism satisfies epsilon differential privacy, and this magical epsilon value here will be natural logarithm of 3, which is easy to verify. That if we simply look at the ratio of these probabilities, what's the probability of answering yes, given that you really, the true answer is yes, versus you answered yes, the true answer is no. So that would be 3/4 over 1/4. And likewise for no, so the ratio is 3, and then so that's e to the power of natural logarithm of 3. And now the number is important here because so basically a natural logarithm of 3 is something that's very close to 1. In the future, I will be showing some practical results from a few DP results, and there, I mean, this level of epsilon around 1 is something where kind of you can get something reasonable done, but it still gives you some level of privacy. And I think this is sort of a good model to keep in mind of what this differential privacy with epsilon about 1 would mean. Yeah, so.
I have a question. If you really do that in a firm, for example, that you would ask about the truck case, and then you get these answers who are answering yes, it seems that it is 3 times more probable that if you say yes, you use drugs than anybody else, then you fire everybody from that.
Well, I mean, you can change the epsilon if you want.
Yes, and there will be, of course, if they would have an epsilon that actually has so that there is no information even for a group level, so that you cannot, it doesn't actually help you in firing.
Yeah,
Is there a system like that?
Sorry?
Is there a system like that? So what is the question answer series that you want to go in such a way that that being answering yes does not make you more probable to actually have to be a drug user.
So the question was, is it possible to
Here,
come up with a mechanism where the probability wouldn't be higher if you are a real drug user?
Yes.
I don't think that probably would be impossible. But I mean, if you require, or I suppose, I mean, you could flip this, that I mean, then you answer kind of converse to what you would do. But I mean, it's not
conversing, then you fire the
yeah.
one that.
Yeah, so I don't think that would be possible. So I mean, there's, in a sense, I mean, there is a fairly general, because I suppose, I mean, it might even be a mathematical theorem that, I mean, if you require perfect privacy, then you can't learn anything from the data. And I guess this would be the case. So if you require that, I mean, you don't learn anything, then you can't. It doesn't leak any information, then you don't learn anything from the data.
I was kind of thinking whether there would be a process that does not kind of then and make it possible to fire this group. So it can learn other things. I don't.
Yeah, maybe that's a separate topic. I mean, of course, I mean, what you can do is that, I mean, if you're not comfortable with this level of privacy, you can tweak the algorithm by using a biased coin that, let's say that there's only 10% chance that you would answer truthfully, then you will get stronger privacy. These will be closer to 1. Or then let's say that there's just 1% chance that you will answer truthfully, and that will control the.
And the more people you have, actually, the more closer those two values can become, because your estimation of the probability becomes so that you can invert the equation.
Yeah.
So if you would have, let's say, 1 million people, you could make it in such a way when they answer the question, they would be a very, very small difference out of it.
Yeah, in a large population, you can guarantee stronger privacy and still get more utility out of the data. Yes, that's right. There's a number of relaxations of differential privacy. I'm just highlighting one because this is something that comes up quite often. So many of the practical mechanisms that we do include. So the mechanism we had before was just this, was basically the same, but without this delta here, or the delta set to 0. But now we allow for a bit of slack here that gives us more freedom to design new algorithms and new mechanisms. And this is something that's often used in practice. And so in case someone has studied differential privacy, there's a sort of commonly propagated misconception that this would mean that basically you have epsilon differential privacy, that epsilon delta differential privacy would be epsilon differential privacy with probability 1 minus delta, which is actually not the case. It's a different thing. So this is a very subtle differences, and there's quite a few of these different definitions. Okay, let's move on to something more practical. And talking about AI, nowadays often is deep neural networks, and neural networks are trained with stochastic gradient descent. So here is basically how you can make stochastic gradient descent differential private. So the assumption here is that we have our objective function, which is a sum of terms, each of which just depends on one entry of the dataset. And the assumption here is that each sample in the dataset comes from a different individual, and we want to protect individual privacy here. So if there are more samples from one per individual, then it gets a bit more complicated than this. Still can be done, but the guarantees you get are weaker. And so in order to make this private, first we need to bound the effect, how much a single individual can have on the result. So we take these per sample gradients. So this is the gradient of the objective, but only a single term. And we clip them in a way that we can bound the magnitude of the gradient. And this allows us to compute the gradient sensitivity. And so without this limitation, this algorithm wouldn't be differential private. And another thing, because often we do stochastic gradients, so we can also do subsampling. It also helps with privacy, because we can benefit from what's called privacy amplification. So this also helps in getting stronger privacy from very large data sets. And finally, we add up these gradient contributions from the data samples in our mini batch, and then add suitably scaled Gaussian noise. And now this Gaussian noise gives you this epsilon delta differential privacy that was introduced on the previous slide. And then what usually happens is that, then the total privacy cost when you repeat this algorithm over a number of iterations can be computed using so-called composition theorems, or there's this moments accountant method introduced by Abadi et al. In 2016 that gives at least very close to tightest bounds that are known at the moment for the total privacy loss over this algorithm. And that's basically it. And yeah, what happens is that you do need to introduce this noise. Also, there is this, in a sense, odometer or meter that's running all the time. So the longer you run the iteration, the higher the privacy cost will be. So there are these trade-offs, and you need to be careful. Basically, anything you do will have a privacy cost, and if you're operating under a fixed privacy budget, you want to meet some final epsilon loss at the end, then you need to be careful about what kind of operations you do in between. So there are some limitations of what you can do, but you can still learn things under this setting. Some practical applications that I've been working on. So the basic setup here starts with a sort of a schematic of DP machine learning. So we have some training data, and we want to learn a predictive model for that data in such a way that we want to guarantee that you can't go back to from the trained model, you can't go back to the original data and can't learn anything. It doesn't, in a way that it doesn't invade the privacy of the training data subjects. And sort of the motivating example that got me into this was thinking about personalized medicine. So I've been working a bit on drug sensitivity prediction, and here we wanted to use differential privacy for this, because obviously with medical data you want to be mindful about the privacy, but then on the other hand, for personalized medicine it would be extremely useful to have a lot of this data available. So here we are looking at a task where we want to predict the sensitivity of a bit less than so we had data for about 1,000 cell lines in all of cancer cell lines, and we want to predict how effective certain cancer drugs would be against these cell lines using gene expression data from these cell lines. It basically measures the activity of different genes in the cell lines. Gene expression data is very high dimensional, so depending on the way you look at it, it would be some tens of thousands of dimensions. And now we have very high dimensional data and only a couple of hundred training data points, so this is a very, very difficult learning problem. Actually, I haven't seen any cases where people would have successfully used something like deep learning for this, because it's simply so small data sets and high dimensional problems that it is just very, very difficult. The data comes from the biggest project that there is in the world, Genomics of Drug Sensitivity in Cancer, where they have measured this for more than 100 drugs. And because this is such a difficult problem, it's actually interesting that linear regression is about the state of the art that you can do with this problem. And that's also what we are using here. Evaluation is something that's commonly done in these problems, is that you look at the ranking of cell lines for each drug, and predicting which cell lines are most sensitive to this drug, which are the least sensitive. And this is makes most sense to look at it this way. And this is what's used in different benchmarks where people have looked at this problem. One feature of differential privacy is that, as I mentioned, the gene expression data is really high dimensional, but privacy in high dimensional spaces is very, very difficult. So we are applying a dimensionality reduction here, and specifically what we do is that we use prior knowledge of which genes are often mutated in cancers, and then picking up a small subset of most important cancer genes based on this, and simply ranking it based on this number of mutations. And this does actually work. It doesn't give you very good predictions, but then again, nothing does. So here's a number of methods that we have compared, and this non-private lasso regression in blue. So these two top lines are non-private methods. The red one here is our differential private method, and then these are other previously proposed differential private methods. So the lasso is actually about state-of-the-art. Lasso regression is about state-of-the-art for this particular problem. So it actually won an earlier challenge using this kind of data. And so we are not too far from it with this epsilon around 1 level of privacy. So using 800 samples, we get about the same accuracy as Lasso would get with 200 samples. So there's a price to pay, but it's not impossible, and we can actually learn something from this data set compared to these other methods that don't really give you anything. But there are a number of challenges, as I mentioned. So high dimensionality is one. We need to be very aggressive in how we reduce dimensionality. More about that in a minute. Then another feature of differential privacy is, if we remember the definition, it's worst case guarantee over all possible data sets. And this means that if your data set could contain some outliers, you may be paying a very high price in order to guarantee privacy also for those outliers, and not just for ones that you actually have in your dataset. So reframing the problem in such a way that you eliminate these outliers can help a lot. In our case, what we did, we introduced actually very aggressive clipping of the data, very aggressive to the extent that it was kind of really clipping most of the samples to some extent. But that really helped a lot, and that was the key thing that drove us from here to here. And finally, one thing is that, this is especially for deep learning. So learning complex tasks under differential privacy from scratch is very hard. So if you look at these classical papers on deep learning, what they often do is that they, for learning a convolutional neural network, they pre-train the convolutions on some other data set without privacy, and only then tune that to privacy on this particular data set. So this kind of transfer of knowledge from a problem where you don't need privacy, that seems to help a lot. That's something we've also done ourselves for this. So this is some unpublished work on getting better predictions on this gene, on this drug sensitivity prediction. So here we are learning a better low-dimensional representation from other public gene expression data using different methods of representation learning. The one that seems to work the best in this particular example is a variational autoencoder. And relative to taking this top 10 genes that was the best in the previous one, we do get quite a sizable improvement here. And unfortunately, this is now on a different metric, but the idea is the same. But again, this kind of idea of thinking carefully about the problem of trying to kind of use different data sources seems to be very powerful and useful for accurate learning under differential privacy. Another interesting topic that we have looked at is about differential private data release. So in this particular problem, we would want to release an anonymized version of a data set. And the way we are doing it is using generative models. So the way we're using it is using generative models. So given some data set, we learn a generative model, and then we use that model to generate new data. And now if this initial part of training the model was done under differential privacy, then we can guarantee that the generated data will be DP with respect to the original training data as well. So effectively, with this approach, we can generate a synthetic data set that has similar statistical properties as the original, but has no identifiable entries. So in essence, it's a new sample from the same population, but you can't link it back to any individual that was a part of the original data set. So here's one example where we've done that on some mobile app usage data. So this is looking at, and there's a few different metrics. So this is looking at frequencies of different app usage, where we get pretty good results, varies with the epsilon. And then this is looking at correlations between different types of app categories in use. And here, well, it's not sure how to really interpret these. But again, I mean, if you look at these plots of these, they look quite reasonable. Finally, I wanted to mention briefly about learning with distributed data, and also about this also links to the question of whether you could use cryptography to protect this privacy. So one approach to privacy is that you use cryptography to train your data to train your model in an encrypted form, and then you get an encrypted. Everything is encrypted, so no one sees the original data, and what you get out is a trained model. And this is good for securing the training process, but it doesn't protect the model that comes out. And as we saw at the beginning, often it can be that the model itself will then also can leak information about the training data set. So I would claim that if we want to protect ensure that the model doesn't leak private information, then we need to have something like differential privacy as a part of our process for developing these privacy-preserving, learning these models in a privacy-preserving manner. But the other side of it is that, in case we do not trust all the parties that are part of the training process, people who have the data, people who are operating the learning, then DP may not be sufficient. And but it can be combined with cryptography to learn these models securely and in a privacy-preserving manner, also with distributed data. So the traditional setup here that most of these algorithms target is the assumption that there is some trusted party who gathers all the data that wherever it is, then runs the learning and then gives a result, and now we can guarantee that this result is DP. You can't get back from that to the original data, but of course we have to trust this one guy here in the middle. An alternative that is used, especially by some of these big internet companies like Apple and Google, is what's called local differential privacy, which is effectively the same as this randomized response, but just done in a larger scale. So every participant in the protocol adds sufficient amount of noise to their own responses before then sharing it with others for learning. And often what happens is, and in order to protect this, especially if it's more complicated than one binary answer, you need to add a lot of noise, and then the results will often suffer with that. But what you can do is combine DP with some secure multi-party computation protocols, which allow you to combine these data securely under this cryptography. And then you can sort of combine the best of both worlds. So you can get the accuracy of the trusted party case, but without having to actually trust anyone with that. So to conclude, one thing to remember here is that these machine learning models and especially more complicated deep learning, powerful deep learning models do remember surprisingly a lot about their training data. And you need to be careful because this can compromise the privacy of the training data subjects. So if there is some potentially sensitive data in there, you should be careful. Differential privacy can help here. So it does provide very strong guarantees. So now in a spectrum of kind of what is good and what is not good, we are jumping from one extreme to the other. So the models do remember some training data, so that's clearly can be not secure. DP, on the other hand, it gives a very strong guarantee to the extent that it's sometimes you have to pay a price for that in the accuracy of the learned models. However, I am hopeful that sort of with more work, and we've also done some of this ourselves, and I mean, we just need to learn these differential private learning techniques better, because I mean, you need to have a different kind of approach for some of these questions, like doing different kind of dimensionality reduction, new view to robustness, and so on. So with that, I do hope that in time we will get closer to the non-private accuracy here. With that, I'd like to thank my colleagues and members of my group who have done a lot of the work. And finally, I realized that in case you haven't heard about it, so, FCAI is organizing the second AI Day in December. And the early registration deadline, I believe, is on Wednesday. So if you haven't yet registered, by all means, please do. Thanks.
Any questions for Antti? Yeah, just a second.
Yeah, so basically the current practicalities of the GDPR. So at the moment, what I've been thinking of doing, at least as my company, is at some level is like once somebody asks that their data should be removed from the system, we would basically just retrain the model without that one person. This is of course quite a large undertaking at each point to do if a lot of people suddenly wish to remove their data, but still it's that's kind of what we've been thinking. So do you know what are the GDPR requirements at the moment regarding this, or do you also, as a second question, do you plan to take this differential privacy to the lawmakers, basically, so that as a kind of an option for everyone to train their model?
I would believe they probably are aware, but I mean, of course, the law doesn't specify any specific technologies. So I guess it's up to the court. And of course, differential privacy also includes this nasty epsilon. And I guess, the only way we'll know what is sufficient is when someone actually goes to court and then asks, so is this particular level okay or not? My answer to this would be that, out of sort of all privacy technologies, I know this is kind of gives the strongest guarantees. So it's probably the best to get started, but kind of what level is sufficient? Well, there's the epsilon. Probably, as you go very small levels, then this should be a strong case. Then if you have a very large epsilon, then I don't know. That's an interesting question for the lawyers. One interesting sort of potential application for this, though, is that I think something people are considering is sort of with this DP data release idea. So with this, if this does work as we would hope, and so we're certainly not the only ones doing this, but if it happens to work for your particular case, then you can sort of create this synthetic, completely anonymized data set that looks like the original. And if it really is anonymized, then the GDPR doesn't apply anymore. And there are people who have been proposing. So let's say that you have a situation where kind of under the GDPR you can only retain the data for a finite amount of time. Let's say you have some old data that you would like to keep, but the GDPR would force you to throw it away. What you can do is to train a model like this, and then you will have this synthetic anonymized version of that data set that in many cases you can use to train models. So we've also done some experiments where we use this synthetic data to train models that do look reasonably similar to what you would get with the original data. So that's one way where this can be helpful. In addition, of course, to sort of training your entire model under DP, in which case I would assume it's probably that the trained model wouldn't fall under the GDPR. So even if someone would ask you to remove their data, I'm not sure. How could they force you to retrain it, because it's just something. It can't be linked. It can't be linked back, so it's not personal data. The trained model is not personal data anymore. But I'm not a lawyer, so please don't.
We have a question here.
So I'm not a lawyer either. I think that if you have gathered data, you have actually asked for a consent to gather it. And then you train your model, and as long as you have the consent for training, you can use it. But then if somebody asks you to remove the personal data out of the thing, you will actually do exactly that, but you don't have to touch your model. So there is this, it's the same thing, for example, if you measure the population of Helsinki and then somebody requires that I want to be removed from that. So that's not, so this aggregates, like a model is an aggregate to a certain extent. It doesn't cover that. But I don't think that they have gone so far that the guys who have written the GDPR actually understand all of this. So there is the part that it has to be kind of it comes out of the system. I have another kind of a question on the system of transfer learning. So have you any guarantees about, so if you go for transfer learning cases, for example, use an image set with 20 million images, for example, to do something and then you have 1,000 images. One would say that the effect on the wages of the new data set may be totally marginal. Even if you do the inference out of that, if you combine it. So would it be a means of actually achieving a better level of differential privacy by adding transfer learning cases even if you don't need them? Just adding extra data that is kind of classifying totally something else.
I'm not sure that I completely followed what you had. I guess, ultimately it goes back to if you want to learn something about a particular data set, kind of, then if it has an effect, then I'm not sure if it helps just adding. If the new data you add doesn't influence the training process, would it change? I would need to think a bit more about that.
So that's why I was asking.
Hey, while we're discussing the deep neural networks, and you mentioned that adding Gaussian noise to the gradients does, to some extent, anonymize it. It's sort of like I find it counterintuitive in a sense that, to my mind, it only would sort of increase the learning time required, but is this something that you've observed, or is there like analytical proof that it actually helps?
in what sense helps? I mean, there is
That increases the privacy in a sense.
There is analytical proof that if you follow that protocol, then you will get. Then what comes out is differential private. I mean that can be formally proven.
Yeah, adding the Gaussian noise does actually.
Yeah, it's an integral part of that algorithm. Of course, I mean the key point here is that, I mean, as you mentioned, I mean it does. You can think that it increases training time, and then kind of, I mean, the more iterations you do, kind of, I mean, you always lose a bit more about the privacy. So that, in a sense, gives you a bound on how much you can learn under a. So if you have a very strict privacy budget, then you can only. Either you have to add a lot of noise at every step, or then you can only take very few steps.
Yeah. Okay, thanks.
Thanks for the talk. I have a question about this differential privacy. I'm pretty new to the field. Is that it's a bit counterintuitive how that will, like, okay, keeping the privacy is one thing, but that's how not we learn. Whereas I will learn from a textbook, like how things work, and then I can separate from what is private and what is not private. But then for learning from the data, I think is it because the learning algorithm doesn't really separate what is a private part and what is not private, so you have to mask something so that it learns, or am I making any sense at all?
I suppose, I mean, one point here is, I mean, linking back to some previous definitions of anonymity, they make this distinction of what are these protected attributes and what are non-protected attributes. The challenge with those is that then, because of correlations between the attributes, you can use the non-sensitive attributes to infer the sensitive attributes. And I suppose, I mean, that's one reason why differential privacy doesn't make this distinction. And the definition really is as it was in the original. So we just look at the probability of obtaining some result from this pair of data sets, and then they should be similar. There's, I mean, this was originally proposed in 2006, and it has taken some time to pick up. But I think, I mean, it's the best thing that we know. It has its weaknesses. I mean, it's not a perfect definition, but it seems to be doing pretty well. But of course, I mean, you're free to develop your own better definition. But it's not easy, because I mean there's a lot of theory and very useful theory behind this.
Right. Yeah. Thank you. I need to read more. Yeah.
One very practical question. You mentioned that you've been doing some research on cancer. Was that right?
Yep.
And so how far off are we with this? So let's say that one of your family members, for example, had their data in this cancer sample, and you would be using one of these models. Would you trust these models to secure their privacy already now?
I would trust it to secure their privacy. Would I would trust it to be useful for predicting what kind of care? That is a much more difficult question.
Okay.
It's a very difficult task, and I mean these are really the first steps toward that. But yeah, I mean in terms of privacy, I mean I do think, I mean, it gives rather strong privacy guarantees. The downside is then that, I mean, the utility you get out of it might not always be kind of very good. But if you want to be sure that this is a good way to sure that the data will be protected, then this is a good way to get started.
Can I have one more question?
Am I wrong in thinking that this Gaussian noise is kind of encryption for the data that we're using, the private data?
Encryption? What do you mean?
I mean, like it's if you have some private data and it cannot be, in a way, get back from the output, that it's in a way encrypted with the. Am I totally wrong?
That would be somewhat a typical use of encryption, because typically for encryption, I mean, you do have an encryption key, and then with a key you can then recover the original. I suppose it could be seen as something like that, but yeah, I mean, I'm not sure if encryption is the word that would commonly be used for that particular. There are some similarities, I guess. Did that answer it, or?
Sure.
So, I mean, for the encryption, typically, so if you were to train these, a method where you would train neural networks on encrypted data, what would happen there is, I mean, you encrypt it, it becomes completely random garbage. I mean, with a Gaussian noise, kind of there's still kind of the mean is 0, and I mean, it's more likely to get things that are similar to the original. So you get some information out of that. Whereas with encryption, if it's done properly, if you just look at the encrypted data and you don't have the key, it will be complete random noise. So uniformly random. You don't learn anything from it. And then this training of neural networks on encrypted data, these are typically based on what's called homomorphic encryption, which basically allows you to compute arithmetic operations on encrypted data. So that is encryption and the arithmetic operation commute, which means that if you add two encrypted numbers, the result will be the same as if you first did the addition and then encryption. And this allows you to, this kind of algorithms allow you to then run complex algorithms like training a neural network on encrypted data, so that the end result will be the same as if you did it without on the original data. But yeah, there's a quite heavy performance penalty you have to pay for that. But it's quite different because I mean in that case, kind of the data you see if you don't know the encryption key is totally random.
Okay.
I think we have one more.
Thanks. It seems to me that the outlier problem might be an issue here. So, how do you? Is it a problem-specific way how you deal with the outliers? So, let's give an example that you live in a city and you're the only one who is wearing eyeglasses. So you're an outlier. So, but you don't know all those kind of outlier classes. How would you deal with those?
I guess it depends. I mean, so far what we've been looking at is, I mean, looking at the data and basically sort of setting some bounds that, I mean, we only look at not too big deviations from the mean. In terms of these classes, I guess, I mean, something we just have to accept is that if there are some very small classes, then under this DP we are not going to get as accurate models for those as we would otherwise. So let's say that, I mean, we are generating these synthetic data and there's some very small classes in the original data set. And I mean, it just I think it's sort of a fundamental property of these models that, I mean, we're not going to get an as accurate a model for this very small minority class as we would for a much bigger class.